Alrighty, so I figured this out. I'm going to explain it. So, this is the problem that we have. The 100 kilogram crate shown in figure 12.5a is originally at rest on the smooth horizontal surface. If a towing force of 200 newtons acting at an angle of 45 degrees is applied for 10 seconds, determine the final velocity of the crate and the normal force which the surface exerts on the crate during this time interval. So this is how I started it, right? We have a 100 kilogram crate, and you can see that's the picture. 100 kilograms, 200 Newton horizontal, force going at an angle at 45 degrees. So I wrote time, t is 10 seconds, and this is our time interval. So t1 is 0, t2 is 10, right? So our vertical force, which now the values are here, that's our vertical force. That's the normal force. Let me turn this off real quick. Yes, there we go. Why did it not work? Forgive me. Vertical force is right here, right? So that is the normal force. So originally I had to look for these. So what did I do? So I have the crate set up right here, right? I drew, this is the free body diagram. So first thing, I mean, you have to come up with a an X and Y position. So I made, conventional X and Y. This is X, or horizontal is X, vertical is Y. That makes sense. And, I think X is usually red when people put colors on them, and Y is usually blue. So that's why, that's the coloring. So X splitting this 200 Newton force at a 45 degree angle. To split that up, you're going to take cosine of 45, since that's the horizontal direction, and multiply it by that 200 Newton. So now this is just the horizontal force. Exact same thing or not exact same thing, but the vertical force is sine of 45, multiplying that by 200 Newtons. Then you have the vertical force. So this is our force down from our mass. So weight is mass times gravity. So I just multiplied 100 by 98.1. Or 9.81. So that's straight down, and the normal we didn't have, which we now do have. But the normal was going up. So the first thing to do was, well, not the first thing to do. Now you have to come up with your conventions of where positive and negative are. So, once again, I just went with like conventional graphical position. I don't even know what you call that. This way, the right is going to be positive, left is negative, up is positive, down is negative. So the only negative value here is that. So you can see here, I split this up. This is the formula we're using, and what this is the principle of impulse and momentum. So this is the when we're just doing what do we call it? It's not a system. This is the for a singular particle. We're characterizing this as a singular particle. It is not a system, so this is what we're using. The mass times the initial velocity plus the sum of the integral from time 1 to time 2 of our force is equal to the mass, again, the same mass doesn't change, unless, I guess, no, it doesn't. It might change if you have a problem. It's irrelevant. Times v2, which is the second velocity, and it asked us to find this. So that's how I knew that this would be the thing that we're using. One, because this was an example question in the unit that was just explaining how to do this. But no, so it was asking for the v final, which is v2. It's the final velocity. So we have this drawn in red corresponding with X and drawn in blue corresponding with Y. So the thing about this that's really, really easy, right? Final velocity is determining the velocity at the final position. Initial velocity is the velocity at the initial position. It's not just So yeah, the final velocity is dependent on the object actually moving. So that's something that I completely forgot about, and I made that mistake, and I went back and corrected it. And I'll explain again what I mean when we get to the Y. But you can see here with x, right? This was a mistake I corrected, but I still wanted to be able to see it. The initial velocity is not this. The initial velocity is before it starts moving. And what is the velocity when it's not moving? 0. So this is just 0. That makes it very easy. And that's the same on both sides for x and y. This is going to be 0. Plus the integral of 200 cosine of 45 times dt. So we're doing that because the only force moving in the x direction, and mind you, this is force, not velocity. That's why I got that wrong. The only force moving in x is this. So that's it. Then it's 100 times v2. And v2 we don't have. That's what we're looking for. It is displaced in the x direction. So that's v2. So this part right here. 0 plus 200 cosine of 45 times 10. So we solve that integral. That's just calculus. You add an x variable and then you multiply, 10 and then minus, that times 0. So that's what this is. I still have that written. It's not exactly necessary since it's easy. Is equal to 100 times v2. And then you just solve it. Divide by 100, 14.1421 v2 for the x. So that is the v2 in the x direction. Now, this is where us finding that in the y direction, as well as the normal force, since that's also in the y direction. So same thing here, 100 times 0 plus the integral of 200 sine of 45 minus the integral, since it's the sum of, remember. That's why we're doing this. It's the sum of every single force that is acting vertically now. So this is why the convention of positive and negative plus and minuses relevant, because this is positive, right? Because remember, positive up, negative 981 down, plus the normal, which is up, is equal to 100 times 0. That's the mistake I made. I did 100 times v2, and then I was left with a formula with both n and v2 in it. And I did some other stuff that was wrong too. This is 0 because, once again, velocity is going to be reliant on the displacement. If it's just, if you're imagining you're towing something with a rope, because that's what this is, it's towed with a chain, you could be pulling it up. It's not necessary, or pulling it partly up. At the end point, it's going to have only moved in the horizontal. It will not have moved vertically, right? Even though some force may be wasted pulling it up, right? It only will have moved in the horizontal. So there's only going to have been a horizontal velocity. Now that we're doing this for vertical, there is no vertical velocity at 0. So it's very easy. You just set that equal to 0. So getting each of these, same exact thing, because it would be 10 minus whatever this is times 0. So it's just, that times 10 minus 0, that times 10 minus 0, that times 10 minus 0. This is what I get, and then you just solve it. Very, very easy. Divided by 10, and this is what I get for the normal force. Since there is no v, because the v is 0, it's gone, that's the only value we have. So when it asks for v2, that's v2. That's the only relevant v2. Now, I am not great with this. This is me explaining my work, right? Provided that we were doing, and if you're watching this video and you know the answer, I'm sure I'm going to solve another one right after this that's going to answer that. But I'm pretty sure if it's moving in both the x and y direction, and it does have both an x and y velocity, say it wasn't asking for normal, and I ended up getting v2x and v2y, and they were both actual numbers, I'm pretty sure I would just do, convert them from because these are both dependent, combine them as I'm trying to think of how to, since it's x this way, y this way, to get this I would have to do x squared plus y squared square root of them, right? And then that would get me this. Pretty sure graphically that's what I would do. And I'm pretty sure that's what you're supposed to do when you're dealing with directional things. But I'm sure I will get that answer. I think that's what you do. Maybe if I'm wrong, correct me. But yeah, that's my explanation. I'm partly posting this because I I want to have a reserve without filling my camera roll up with junk. But yeah, that's how I did it. If you want to look at this again. yeah, that's the, and there is an explanation on here too.